Okay, so hello everyone, and welcome to the ICTS String Seminar. Today, we're very happy to have Felix Haehl, who will tell us about the P-spin glass model, a holographer's perspective. So please, Felix, take it away.
All right, so thank you very much for inviting me and for showing up at this late time for you. So I'll tell you about this paper, this recent paper with Tarek, Anus, who is at Amsterdam. And I should give you the disclaimer that my background is in ADS-CFT and holography and so on. So I'm myself a little bit new to this subject, and I can already see that there's people in the audience who have much more experience with spin glasses than myself. On the other hand, this is a string seminar, so part of the point of this talk and this project is to introduce the subject to the HepTH community and ask about connections with gravity. And in this spirit, I'm going to be reviewing quite a few things that are hopefully new to many of you, but that might be old to some others. So one of the reasons I got into this subject is because of the many exciting developments in low-dimensional holography in the past few years, and many of these developments have some perspective where they have something to do with the replica trick and its manifestation in gravity, and then certain types of wormholes and so on. And as I will discuss, spin glasses are about the replica trick and about replica symmetry breaking. So this is an extremely interesting phenomenon that we were hoping to understand in ADS-CFT eventually. But before doing that, we felt we really need to understand this in quantum mechanics better. So given the audience, my introduction will be a bit from the point of view of what happened in the HepTH community in the last few years, in particular from the point of view of the SYK model. And I'll talk a bit about the connection with gravity. And then I will introduce this P-spin model and various features of it and various signatures that might be reminiscent of gravity. And in the end, I'll speculate a bit more about connections with holography. All right, so let me remind you of this SYK model, which has informed much of our recent understanding of holography in low dimensions, and which sort of serves as the background for this project. And I want to recall a few features of SYK that underlie this connection with gravity. So the SYK model is this model, this ordered quantum mechanics model of n Majorana fermions, which is a bit special in the sense that it's solvable at large n in terms of some bilocal master field G that effectively becomes some sort of classical variable. So I cannot get rid of this thing. Okay. Comes a classical variable at large n, and you can solve the model exactly in some sense. And this attracted a lot of attention because it's a solvable toy model of holography. And one way to understand the connection with gravity and with black holes is through the strange metal properties of this system, if you want. Or, well, let me just say that at large, so if you consider the strong coupling limit of this model, large beta J, where J is the average, has to do with the average of these random couplings, then you find an effective action for this variable G, which develops a conformal symmetry, or it differs one symmetry, a reparametrization symmetry in time. However, if you solve the saddle point equations, you find that the solution breaks this symmetry. And what is left is an SL2R symmetry. So we have a spontaneous breaking of this reparametrization symmetry. And it is the symmetry is also explicitly broken by this Schwarzian action that you've probably seen before, which describes the cost of exciting these pseudo-Goldstone modes associated with reparametrizations. Now, this Schwarzian action, of course, also appears in gravity in particular in this Jakiv-Teitelbaum model of dilaton gravity in ADS2, where this particular action describes the boundary degree of freedom associated with the dilaton. So the connection with gravity is very explicit here. Of course, a complete holographic and in particular a microscopic understanding of this connection is still missing, but many of the features at low energies are described with this JT gravity model. Now, another consequence of the symmetry breaking pattern, and in particular of this SL2R symmetry that's preserved, is that you can use it to compute the entropy and other thermodynamic quantities at low temperatures. And then you find that the leading contribution, let's say, to the entropy, okay, so first you have a ground state energy and an extremal entropy. But then there's a term in the entropy which is extensive in n and linear in the temperature. So it goes like 1/beta. And this term is associated with the Schwarzian action. So you can just think of computing the free energy as the on-shell action. And then you find this. Another way to think about it is as the specific heat, this term, which then is linear in T. And that's, of course, another well-known consequence of this conformal symmetry structure. Now, finally, let me mention one more observable that we've been interested in, and which makes clear this connection with gravity, and that is something you see in the 4-point function. If you compute 4-point functions in this model, and you can ask, so you compute a 4-point function in the SYK model, and say you can ask what is the contribution of the Schwarzian mode to the 4-point function. You find it describes a universal contribution to the 4-point function, which is particularly interesting in some out-of-time order configuration. So let me very briefly talk about that because it's going to be important later on again. So yeah, just in case you're not familiar with this, so the reason people are interested in these 4-point functions, in particular Lorentzian configurations, is that these serve as a way to quantify chaos, a quantum notion of the butterfly effect. So the idea is that you start at some time t and evolve backwards in time, insert a small perturbation in the past, and evolve forward again. It's the usual setup for chaos. And if the Hamiltonian of the quantum system is chaotic, then even a small local perturbation completely disrupts the cancellation between forward and backward evolution. And you end up with a complicated many-body operator, psi of t, even if the initial operator at time 0 was simple. So to make, or in other words, the time evolution introduces all these commutators with the Hamiltonian. So the operator grows and gets more and more complicated and has overlap with many operators in the theory. So to make this more precise, you can compare two states in the theory. And in both of these states here, we want to consider two operator insertions, one at time 0 and one at time t, but we swap their order. So we ask, does it matter in which order we insert them? And the one we insert at t feels this chaotic time evolution of the Hamiltonian. So to compare how different these two states are, you can compute their overlap. And that is going to be a 4-point function. And this 4-point function, so this 4-point function, or some analytic continuation of the 4-point function, looks like this. So it's out of time order in the sense that in this complex time plane here, you have to go back and forth several times in real time to insert the operators in this particular order. Okay, so, and it's clear that for very small t, let's say the two operators commute, then these two states are essentially the same. And the 4-point function you get is like a product of 2-point functions. But as you wait longer, and if the Hamiltonian time evolution is very chaotic, then even though these states were essentially the same at early times, they start differing a lot. And you see this in the growth of this connected contribution of this out of time order 4-point function. In particular, the growth will be exponential. That's going to be our signature for quantum chaotic evolution. And due to this 2015 paper here, we know that there's a bound on how chaotic it can be. In particular, there's a bound on how large this Lyapunov exponent, this quantum Lyapunov exponent can be. The maximum, the fundamentally maximally allowed value being this 2 pi over beta. And the reason this is interesting from the gravity point of view is, of course, because black holes are fast scramblers. And so black holes, classical black holes, saturate this bound. And so does the contribution to the 4-point function in the SYK model that you get from the Schwarzian action. So, okay, so that's the third connection with gravity that I wanted to recall. Is this clear so far? Hopefully known. All right. So now what I'm going to talk about in this talk is a different model, which is not SYK, but it's similar in some respects. So it also has random disorder. It also has these random couplings between some number of spins, but the spins are going to be bosonic spins, sigma I, instead of Majorana fermions. And we will have to constrain them to live on an n-dimensional sphere. So that's something you have to do when you consider bosonic spins, because otherwise there's runaway directions in the potential. So let me talk about this very schematically first, and then I'll give you more details. But so at a schematic level, when you think about doing this, considering these bosonic spins and constraining them to live on a sphere, you're going to end up with 2 couplings. One of them is the same J as before, or the dimensionless combination beta J, that describes the strength of these interactions, or the inverse temperature. And the other coupling I will call MJ, and that roughly you can think of as the size of that sphere that we constrain the spins to live on. And its physical meaning is going to be that it parameterizes the strength of quantum fluctuations in some sense. So we have 2 couplings that tell us about the strength of thermal fluctuations and quantum fluctuations. And it's going to be interesting to observe how they interact with each other, what's their interplay, how do they affect various features of the model. Now, so one thing that these models with quench disorder have in common is the randomness of the potential. So you have all these random couplings J, IJ, KL, and so on. And every spin or all the spins talk to many of these couplings, so it's very difficult to minimize the energy. So what you should have in mind is some energy, some landscape of free energies in these models that's extremely complicated and rugged with many local minima and valleys and spikes and so on. So a very complicated energy landscape, and the system somehow tries to find the minimum in this landscape. And what happens in spin glasses is that there's a phase transition as you lower these couplings and make both types of fluctuations weak. Then the system somehow gets stuck in one of these valleys. So it moves around in this complicated free energy landscape and it gets stuck somewhere, and the spins freeze in some state which is locally stable, but it's not the lowest energy configuration. So the system has many metastable states, and it takes a long time to move around between them. So the system loses ergodicity, and the accessible states become uncorrelated, and random matrix theory predictions fail, and so on. So this seems like a very complicated state of affairs, and of course it is. But certain mean field methods have been developed that allow us to make progress and to understand some crucial features of this phase. So in particular, there again exist more coarse-grained order parameters that characterize this state. And a particularly useful one will be this order parameter that goes back to Edwards and Anderson that I'll denote by U. You can call that the average self-overlap, for example. So it's like a 2-point function. We need to consider something quadratic, something like a 2-point function, because the average magnetization of each individual spin just vanishes after you average. But if you square them in this way, the square can still survive the disorder averaging. And similarly, yeah, so this will serve as an order parameter, and if this quantity vanishes, we're in the what I call the paramagnetic phase, which is contrasted with the spin glass phase, where this order parameter is non-zero. And to make this a bit more concrete, I plotted here something more dynamical that you can have in mind.
I have a question.
Yeah.
Could you comment? Could you explain once more this need to put them on the sphere? Like,
sorry, can you say that again?
So could you explain this comment that like one has to put these spins on the sphere? What does it mean?
Yeah. So in 2 slides, I'll give more details on. I'll define the model in more detail, and then it will probably be more clear.
Thank you.
But so the basic idea is just that you have bosonic spins now. So you know in such a bosonic system, if you have random couplings which have random signs as well, then you can have runaway directions in the potential. So you have to constrain the spins to live on a sphere such that this doesn't happen. The system is stable.
Does it mean the sigma I like squared sum over everything is 1? Is that the constraint?
Yeah. So that
Thanks.
yeah, I'll write that explicitly in a minute. Yeah. I'll just finish with this qualitative intuition slide, and then I'll get to the details.
I have a question.
Yeah.
So the sigmas, they are bosonic spins, and they can point in any direction.
Yeah.
So they can't be electrons. Because electrons have only 2 spin directions.
Yeah. So they're like.
So
But so the sigma I, you can think of these sigma I as the coordinates on a high-dimensional sphere. It's a sigma model.
So they are not fermions.
No,
They're bosons.
they're now bosons.
But even bosons have discrete spins. They can't have continuous spins.
Yeah, I hope this will be more clear once I write the actual model.
Okay, go ahead.
Perhaps, yeah.
Go ahead.
Perhaps you should wait 1 slide and then I'll actually write down what the model is. Yeah. Then maybe this will. Yeah, let me just say one more thing about this order parameter. So this is something that you can see dynamically if you consider something like a 2-point function, where again this overline denotes the disorder averaging. And then you see that. So I plotted this at some fixed temperature here for different values of this coupling that parameterizes the size of the sphere or the strength of quantum fluctuations. And if this coupling is small in the first case, we're still far away from the spin glass transition. And you see this sort of oscillatory behavior, which you can think this comes from the strong quantum fluctuations. And then in this middle picture, we're approaching the spin glass transition, and you see this interesting decay that has some interesting structure, and which comes from the competition between the thermal and the quantum effects. And in particular, you can see it slow down. So the dynamics slows down, and the system takes a longer time to equilibrate. And then finally, in this last case, I plotted what this 2-point function looks like below the spin glass transition. And now, in some sense, the dynamics freezes in the sense that this 2-point function doesn't reach 0 ever. So it just decays to some constant value, which coincides with this order parameter u. Okay, so that's one dynamic consequence of this freezing. Okay, so the goals are going to be to take some of these characteristic features, like this slow dynamics and the fact that there's many states in this free energy landscape, and that the system is having a hard time to reach equilibrium and it loses ergodicity and so on. So we want to understand some of these features, and we want to see how do they interplay with some of these chaos characteristics, such as out of time out of 4-point functions. We want to see, is there still some notion of a conformal symmetry? Is there an emergent reparametrization symmetry? And there will be. And then eventually, can we incorporate all these features in this ADS2 NCFT1 paradigm, where and can we come up with a holographic description of this? All right, so here's the model now in more detail. So this partition function as a function of any choice of couplings defines the model. So the basic variables are these sigma I spins. These are the bosonic spins, and the spherical constraint that you asked before is this condition here that we implement using a Lagrange multiplier Z. So there's a Lagrange multiplier that implements this constraint, and this is what I meant by saying that these spins live on a sphere. Okay, that if you sum of all the spins, the square of all these spins gives you n in some normalization. And the other coupling, this coupling m that I mentioned, shows up here as the coefficient of the kinetic term, which in SYK you were not free to tune that was fixed, but here it's a free parameter because of this spherical constraint. So we cannot, you can rescale this m away here, but then it's going to show up here. You cannot get rid of it. And the random couplings J are distributed like this and give you these interactions. Okay, so we have our 2-dimensionless parameters, and the whole thing is a nonlinear sigma model with a fixed size spherical target space. And this spherical constraint is really, I mean, it's clear that it's needed, and it's going to be really crucial for the physics we're going to see. Now, the first goal when you presented with this is to compute this order averaged free energy. So we take this, we take log Z and average over couplings. And the tricky thing is that we have to take log Z first and then average over couplings. Okay, that's what makes life harder here, but more interesting. And the usual strategy for doing that is, of course, to use the replica trick. So we write log Z as the limit as n goes to 0 of dn z to the n. Then we can replace log Z here by powers of Z, and to compute this order averaged free energy, we only have to compute the average of powers of Z. Okay, and the average of powers of Z, that's easier to compute, so we can do that at large n, and we get some expression. But the new feature now is that everything has this index A, the replica index, that tells us on which copy, or on which of these n copies we are. So the collective variable that we consider now, the thing that was called G before on my SYK slide, I'm going to call Q here. And also that 2-point function is going to carry in replica indices A and B. So there could be 2-point functions between different replicas. Now you do this path integral, you integrate out the disorder, and you integrate out the spins, and then you get an effective action for this Q variable. And okay, I haven't written the effective action here, but there's a Schwinger-Dyson equation, which is written here for this matrix Q. And some of the features here, especially some of you might be more familiar with the SYK model. So there are some features here which are different and important. So the first one is that the Q for not equal replica indices, so the correlation between replicas, can be non-zero now because we have bosons. So we can have 1-point functions here, and this can become this self-overlap that I was talking about before, which might be non-zero in the spin glass phase that we'll be interested in. Another feature to note is that the kinetic term now has 2 derivatives and a coefficient m that's a parameter of the model. And finally, we have this Lagrange multiplier z. It also shows up in the equation of motion, and that's going to play an important role. So this Lagrange multiplier was responsible for implementing the spherical constraint. Now, how do you solve this equation? There's a well-known strategy for doing that. And what you do is you make an ansatz for this Q matrix, for the structure of this Q matrix. And the ansatz that one can show is the right thing to do. Is this one-step replica symmetry breaking ansatz where you put along the diagonal of this 2-point function, you put some variable Q, or Q sub r here, which is our 2-point function, and you add to it some block diagonal matrix. So it's an n by n matrix, right? So we had n replica copies, and in this matrix you put m by m blocks. So there's a new parameter of small m that tells you how big are these blocks. And in these blocks you put this Edwards-Anderson parameter u that I mentioned. Now you could also put some parameter s on the off diagonals, but you can show here that this s you can consistently set that to 0. So we really just think of these green blocks as non-zero and filled with some constant u. And so this is one-step replica symmetry breaking. There's higher step replica symmetry breaking where you refine this ansatz and make the blocks give more structure to these blocks. But in this model, this is not necessary. And this ansatz actually describes the most general thing that's required. So from that point of view, this is one of the simplest models of a spin glass that you can consider, because this replica symmetry breaking structure truncates. Now, yeah, so the meaning of this u parameter is that it tells you the overlap that you have between replicas. And so this diagonal time-dependent thing is the self-overlap within any replica, and these u's tell you the amount by which replica symmetry is broken, and you have overlap between replica copies. And in this n to 0 limit, these parameters might stay finite. And this, yeah, so all these parameters are going to show up in the equations of motion and in the various dynamical things you compute. Good. Yeah, please interrupt me if anything is unclear. Okay. Now we take this ansatz for this QAB matrix, plug it into this Schwinger-Dyson equation, and you get some equation of motion. You can rewrite that equation of motion, and in Matsubara frequency space, it looks like this eventually. So this is a nice way to write it, where you see that there's some automatic renormalization going on, in the sense that these 0 modes are subtracted from the k-dependent, from the frequency-dependent terms. You also see that this equation is empty for k equals 0. So there's an additional equation for the 0 mode for the q hat, the Fourier transform. At 0 frequency, there's an additional equation which I didn't write, and then there's another equation for the parameter u. It shows up in this matrix, so you can also vary the effective action with respect to that parameter and get another equation. So there's a few equations that are coupled, and then you have to solve. But these two other equations are algebraic. Now, what about this parameter m? There's this, the size of these blocks was m. How do you determine m? So one thing you can do is you can again vary the effective action with respect to that parameter and extremize. I'll sometimes refer to that procedure as equilibrium spin glass, but this turns out not to be quite the right thing to do. So, and in some sense, the fact that the glassy phase it doesn't reach equilibrium, in some sense that can be thought of as having to do with the fact that we do not impose this extremization later. But I'll get back to this subtlety. So for now, let's just run with this, and then I'll get back to how to determine m more properly.
Question.
Yeah.
So this the sigmas, are they supposed to be understood as some sort of expectation value for the Pauli spin operators with respect to so the physical states, because then they can point in any direction. But if they're just operators, then I don't think they can take any arbitrary direction.
These sigmas are just classical spins, right? I mean
Classical
they're just,
so they have to be expectation values with respect to some states.
They are just classical n-component vectors, which take values on the sphere. That's it, right? Is that right, Felix?
Yeah, that's good.
No.
So there's no. You're not taking any expectation values of any Pauli operator here.
No, but how can? But spins are not classical; they're quantum.
Maybe I can comment. This is Subir Sachdev. So this is some effective model for some quantum degrees of freedom. And even if you take the sigma and you quantize it on a single site, you get a bunch of discrete levels. You can think of those levels as, the two lowest levels as the levels of an Ising spin in a transverse field. And then, but it has extra levels at high energies, and those eventually don't matter for the structure of the low energy physics. So if you just take the kinetic energy of this particle on a sphere and you quantize, you get discrete levels. So you just work with the lowest few levels, and then you can model an electron in a magnetic field.
Mm-hmm. Thanks. Okay, I hope that helps. Yeah, let me go on. So, okay, maybe I have to. Yeah. Anyway, so you can solve these equations numerically. The equations that some of them I wrote and some of them I didn't, and you find some phase diagram. You find that this transition to the phase where u is not zero happens, and it happens in some region of parameter space where temperature is low and this mj is large. So what I plotted here is actually the value of m, this quantity that we'll have to talk more about. That tells you how large are the blocks in this RSB ansatz. Okay, it's not. Yeah, the details here are not so important. Let me just move on. Now let's get to this reparameterization symmetry. And before I talk about the spin glass phase, let me briefly talk about the paramagnetic phase. So the phase up here where u is 0, m is 1, and we're not in this glass phase. Okay, so in this case with unbroken replica symmetry, many things are, mathematically quite similar to SYK. For instance, if you consider this large beta j limit, the equation of motion becomes this expression, which might be familiar to some of you, where lambda here lambda here is the self-energy. So it's called sigma in SYK. Okay, and this equation, this strong coupling equation, you can check as a reparametrization invariance. So sending tau to some arbitrary function of tau, which is spontaneously broken by the by the saddle point. So this conformal scaling solution breaks that symmetry, and then you get a Schwarzian action and so on, the same as what I sketched in the beginning. But so that's nice, but the problem is that this conformal solution here is actually not stable. So here it's where it's different from the SYK case, that this solution is not physical in some sense. One way to see that is by computing the spectrum of, by actually thinking of this as a CFT and considering perturbations to that CFT, and computing the spectrum of operators that appear in the OPE of two of such spins. You can do that exercise, and this spectrum of operators is going to be determined by the conformal symmetry. So if you do that, you find a tower of possible operator dimensions that can show up in this OPE. So the first one is this H equals 2 mode. And then you find all sorts of irrational dimensions that you can get. But in addition, the thing is that you find an operator dimension in this OPE that is complex, and that is one signal for this solution, that this solution is actually not stable. And indeed, if you solve the equations numerically, you find that there's another solution. There's a physical solution to these replica symmetric equations, which is the stable one, which is the physical one, which is also thermodynamically preferred from free energy considerations. But it has no conformal limit, so it doesn't have this scaling limit, and it behaves completely differently. It's gapless and so on. And you have to construct that numerically, and that is straightforward to do. So you just solve the equations numerically and focus on this physical solution. And I sort of show here what it looks like. So this is on the left. This is what the solution looks like, what the 2-point function looks like in Euclidean time, the Matsubara 2-point function. And you can also consider the spectral density via this usual relation. You can ask what's the spectral density corresponding to this 2-point function. And it has some interesting behavior, again, as a function of these various couplings in the model. So the typical behavior is like, say, this yellow line, where the spectral function has a gap, and then there's some excitation. But you can ask if you fix the temperature and just lower this, or increase this coupling MJ. So that means going closer to the spin glass transition. So what we saw before, where the dynamics slows down and you have this 2-step relaxation and so on. So as you go closer to the transition, you see that in the spectral function, sort of the gap gets smaller, and sort of there's now more low energy excitations. Okay, but what we're really interested in is this glass phase. Okay, so let's see what happens there. If we're below the glass transition and we have a replica symmetry is broken, so this U parameter is non-zero and all that. So this was the main equation of motion that we had to solve. And now let me remind you that Q, so the full spin 2-point function, I split it into this constant order parameter that is now finite, plus some time-dependent piece QR. And in the strong coupling regime, this QR is much smaller than U, so the solution is dominated by that constant value. So we can do a perturbation theory, a perturbative expansion in this parameter, in this time-dependent piece QR. In particular, we can take this self-energy with all its u dependence and expand it for small qr. Okay, and in this perturbative approach, the equation of motion, we can again solve it analytically. So let's do that. So this is valid at strong coupling. And if we just keep the first term in this expansion of the self-energy, we get some approximate solution, which we can write down analytically. So it's some completely explicit thing, which I wrote here in frequency space. Yeah, so gamma is some parameter that depends on the zero mode. So as you can see, the zero mode plays an important role. It shows up all over the place. Now, this approximate solution is quite nice. So first of all, so let's consider this approximate solution at high and low frequencies and see what it behaves like. So at low frequencies, to leading order, you get the zero mode, you get a constant, and then the subleading term goes like absolute value omega. So that's associated with a conformal scaling solution. If you Fourier transform just that term, you get a conformal solution that goes like 1 over tau squared. So it's associated with some marginal dimension 1 operator that has appeared. Okay, so we have the conformal limit. There's a conformal solution in this spin glass equations. But this approximate solution does more, because also at high frequencies it's well behaved. In particular, it's finite at high frequencies, which means that we can consistently impose this boundary condition. Okay, so you can imagine that we have this approximate solution, and it's a good approximation both at high and at low frequencies. So in some sense, it's yeah.
I have a question. So gamma is smaller than the frequencies you consider, like in this expansion?
Yeah, so the combination gamma omega is in this expansion here would be small. Yeah. So gamma is goes roughly like 1 over j.
But like you don't have to compare gamma and omega in some sense.
Gamma is yeah, I think gamma omega is small. Well, yeah, gamma sets the scale for this. Yeah. Yeah. So the only assumption I needed for this to find this thing was that that this is valid, and this sort of translates into the statement that MJ is large.
Okay, thank you.
Yeah, and then here I have 2 different expansions for small and for large frequencies. Okay, it's maybe more useful to plot this. So here I just plotted this approximate solution. These are the dotted lines. And you see they fit very nicely to the numerical solution, both at short and at long distances. And you can use this approximate solution to compute various other things. For example, the spectral density here on the right. And again, so the spectral density for this approximate solution has this square root behavior. And again, it matches quite nicely to the numerical solution, especially for these red lines, for instance, where the temperature is very small. Okay, so the fact that we have this approximate solution, and in particular the conformal limit of it, means that we have various properties of the conformal of this reparameterization invariant systems. Now there was this subtlety about M, about the size of these blocks. Okay, I think I should speed up a bit, but let me mention briefly that this conformal solution that I just described if you compute it, it just gives you a value for m without solving an equation. And the value that you find doesn't extremise the free energy. So it does not satisfy this extremization criterion that I had before. And in fact, it's useful to think of this block size m as some external thermodynamic parameter. So that's one way to think about how this happens and why this makes sense. To elevate m to some thermodynamic parameter that's similar to temperature, or maybe more like 1/, temperature, that we can tune to the value required for a solution to exist. And you can make sense of this by considering a thermodynamic ensemble where it's sort of some kind of grand canonical ensemble where you consider m physical copies of the system. So these are not replica copies, but you physically clone the system m times. And then on top of that, you do the replica trick to compute log z. But before you do the replica trick, you physically clone it m times. And you have this m as a free parameter that you can tune. So then the thermodynamic variable that's sort of dual to this m in this ensemble is an object that's often called complexity. And it's an entropy, that's like an entropy, right? It's kind of like an entropy, and it counts metastable states. So it's a measure for how many of these metastable states we have in our free energy landscape. So it plays a very similar role to the entropy in more standard thermodynamics. And you can compute this complexity that's dual to m as a thermodynamic parameter, and you get some result. It's maybe interesting to note that this complexity vanishes for p equals 2. So remember, p was the order of the interactions, like the number of indices of j. So for p equals 2, we might expect that the system behaves very differently, is not chaotic, and so on. And one signature of this is that this complexity, then this entropic quantity, vanishes for p equals 2. Okay. Yeah, let me skip that. There's another way to think about m. Now, let's try to get back to gravity. So the spin glass, as I tried to explain, the spin glass has emergent conformal symmetry. That's strong coupling, and the way you see this, but it's a little bit unusual. So you have the exact 2-point function has this constant background value that describes the non-ergodic behavior of this phase. And on top of that, you have the scaling solution. But the scaling solution determines much of the physical properties. So there's a reparametrization symmetry, the spectrum is gapless, and so on. And also there's an extensive number of nearby states. So similar to the entropy we talked about in the beginning. But now we have to consider this generalized quantity, which is not just the entropy density, but also this complexity that accounts for these for this large number of states.
I have a question regarding the replica trick.
Yeah.
So why does one need the replica trick? Because log z need to be written as a limit of the kind of thing that you have written. It can be written as the integral over a Schwinger parameter dt over t times e to the minus tz.
Mm-hmm.
Where t goes from 0 to infinity.
Yeah. So there's.
So I mean, if you write it like that, then there's no need for a replica. Can we just evaluate it by the usual method of evaluating e to the minus beta z?
Yeah. So there's other methods to do these things. The replica trick is not the only way you can compute these quantities, but it's the one I'm focusing on here, because you might think that it has some meaning in gravity, or that you perhaps know something about how to do that in gravity. And
even e to the minus beta z has a partition function interpretation, right? So even that can have a gravity interpretation.
Sure. Yeah. So yeah, it might be interesting to see if other approaches would be just something useful. Yeah. I'm just considering this particular approach here. And you know, the quantities you get in the replica trick, this U and M and so on, they're physical. They're not, you know, you see them in physical observables.
But they might be artifacts of the replica trick.
Yeah, but
I mean,
you can,
you don't need to do it that way.
You don't need to do it that way. That's right. But you can do it that way, and you find, you know, you get the same results in the physical. You get things that you can physically measure.
Yeah, but I mean, are there experimental signatures
sorry,
for such things?
Maybe we should let Felix finish because his
Okay.
time is running out, and leave this discussion for the end.
Yeah, let me try to get to this four-point function. Okay, we can get back to it afterwards. So the last quantity I wanted to talk about is this four-point function and quantum chaos. So the four-point function concretely is a four-point function of these spins with pairwise equal indices, and we'll be interested in the connected piece of that. Sorry, I'm not sure if this is correctly normalized, but you know what I mean. We want the connected contribution to this, which you can construct recursively from ladder diagrams. So you can draw the diagrams that you get from the effective action, which contribute to this four-point function. And these are these type of ladder diagrams where the four operators sit at these edges, and the rails of the ladder get connected with these rungs that constitute of p-2 powers of this thing. So there's roughly like the self energy. It's the interaction term in the effective action that gives these rungs. And the ladder kernel, the thing that you have to do this geometric series of, takes this particular form. So you get that from the quadratic action of fluctuations. You can compute the quadratic action, and the kernel is this k. And perhaps an interesting object to keep in mind is, so this k has this term, which is p-2 copies of qr plus u. That was the two-point function. Those are these green rungs. But then it also has these rails, and these are also offset by some parameter v. And this v is some sort of four-point version, perhaps, of this Edwards-Anderson parameter. So it's something that's also built out of m and u, and depends on the order of the couplings. And it offsets the rails in the spin glass phase, similar to how the two-point functions were offset. Now, this was the Euclidean thing. Now you can analytically continue and consider the real-time four-point function in this out-of-time order configuration. And if the system is chaotic, we would expect this to grow exponentially. Now, so here's the real-time version of this ladder kernel. And so the simple way to solve this problem, or to extract the quantum Lyapunov exponent, is just to ask what's the condition for exponential growth. And the condition for exponential growth is that adding one more rung to the ladder here does not change the result. Okay, and that condition precisely means that the four-point function should be an eigenfunction of this kernel with eigenvalue 1. Okay, so the kernel acting on this connected four-point function gives you back the four-point function. That's the condition for exponential growth. So all we have to do is solve this exponential growth condition. And we can do that in two ways, or we did it in two ways. One is perturbatively in this conformal limit, using this approximate solution that I described, and working perturbatively in large couplings. And the other way is numerically. But yeah. So let me describe the analytical way first, because it's maybe more illuminating. So we try to solve this equation given this retarded kernel. So we make an ansatz for this four-point function, a growth ansatz. So we make an ansatz that this grows exponentially with some Lyapunov exponent that we need to determine, times some function of the time difference. So that's the piece that does not grow exponentially. And now we can do conformal perturbation theory around this approximate solution. And if we do that, then this equation here just turns into a Schrödinger problem. Yeah, I think so. I should say similar things were found by people who I think are in the audience. So yeah, so we find so this exponential growth condition turns into a Schrödinger problem, and as a Schrödinger problem, it's well known what are the energy levels of that. The energy levels translate. So the energy is here the right-hand side, and that translates into allowed values of the Lyapunov exponent. And we find that there's precisely one allowed value which is positive, and we can compute it perturbatively. So again, it goes like p minus 2, so it vanishes when p is 2. It's leading order, it's linear in temperature. Well, okay, so this is beta over 2 pi, the maximal, this is Lyapunov exponent divided by the maximum exponent, goes linear in temperature. Or another way to write it that's kind of interesting, but I'm not sure what it means, is that it's proportional to m. This replica symmetry breaking parameter m shows up 5 times m over 24. So that's a very simple approximate expression at strong coupling.
So just a quick question. Shouldn't that be bounded by 1?
Yeah, so I plotted it here. These dotted lines are this result, and you can see these are, so first of all, they go to 0 at strong coupling. Then they grow, but at some point this approximation breaks down.
So it's always, okay.
So this is just an approximation at low temperature.
Yeah, sure, okay.
Okay, so here is a more complete numerical plot. These are just the values of the Lyapunov exponent that we find, divided by the maximal exponent. On the x-axis, I have this parameter mj that tells you how strong are the quantum fluctuations, and the different lines correspond to different temperatures, beta j. Yeah, so there's a lot happening in this plot. Let me try to explain a little bit. So here on the right, we're in the deep paramagnetic regime, far above the phase transition. So here, as we go further to the right, we go further up in this phase diagram I had. So the quantum fluctuations become very strong, and the Lyapunov exponent approaches 0 asymptotically. Then here on the left, we're in the spin glass phase. So these dotted lines, that's where the transition to the spin glass happens. And then interestingly, we find that the Lyapunov exponent is not 0 in the spin glass. So there's still some modes that scramble efficiently. It goes to 0 here in the strong coupling regime, but then there's some finite value for the Lyapunov exponent. And down here, well, okay, so somewhere here it's captured by this approximate solution I described. And then another interesting feature is this peak here. So this peak tells you something about the dependence of the Lyapunov exponent on the coupling mj. Okay, so in each of these curves, there's a fixed temperature, but for different value. But now we look at fixed temperature. How does the Lyapunov exponent depend on mj? And it has this interesting peak. So there's some interesting behavior on the coupling mj, and this is sort of also correlated with the structure of the 2-point functions and the spectral functions I showed before. So over here, the spectral function had this very clear gap. And then as you go to here, we saw that even in the paramagnetic phase, the gap gets very small, gets smaller and sort of closes. The dynamics get slower. And this peak has to do with the transition between these two regimes. Okay, so you can read off a lot of interesting information from these exponents. Now, I guess I'm out of time.
I mean, it's fine. You can take more time if you need. I mean, how much time would you need?
Well, I think it's maybe just 2 slides. And then
yeah, I mean, feel free to take more time.
So this is just some suggestion about the gravitational interpretation. yeah, so we saw this interesting features that there's this conformal symmetry and there's lots of metastable states. And there's a non-zero Lyapunov exponent, but all these features were a bit different than what we saw in the ADS2 CFT1 and in this holographic paradigm. We had this constant background value on top of the conformal solution, and we had to talk about this complexity in order to really count these states. And the Lyapunov exponent vanishes at strong coupling, at least in a particular strong coupling region. So everything seems a bit different, and it seems that we need a bit more than the known tricks to accommodate for all these effects in ADS CFT. So the question is, how do you do that? And we certainly don't have an answer yet. And the following is just a suggestion, and we haven't worked out any details. But let me tell you the suggestion. The suggestion would be that this has something to do with ADS2 fragmentation instability that was studied. Well, in particular in this paper, Modus Dynamicus and Strominger, and it's based on the existence of a solution to 4D Einstein-Maxwell theory. So the simplest example would be that you consider two Reissner-Nordstrom black holes in two extremely Reissner-Nordstrom black holes with some charge in 4D Einstein-Maxwell. And then there's this nice exact solution. And this solution has the property that it has it has various free parameters. So you can in this potential V, you can add more terms that go like different charges centered at different locations, x1, x2, x3. And asymptotically, as you make x very large, these geometries look the same as a geometry with a single throat, a single horizon, and a total charge Q1 plus Q2. But as you zoom in and go with x close to x1 or x2, you see that this ADS2 space fragments into several throats associated with these different charges. So we hope that perhaps these features are reminiscent of the spin glass phase that I discussed, that there's a large moduli space of such geometries, which are local minima of the free energy. So by varying these parameters xi and qi, you can construct all these different geometries, and they're all exact solutions and so on. And perhaps you can count them somehow with some quantity that's like the complexity that I described. And another point to mention is perhaps that this fragmentation of this ADS2 space, as you zoom into these x1 and x2 horizons, you can detect that asymptotically, not in the total charge, but in the presence of some dipole moment. Okay, so you have some multiple moments in the electric field, in the electrostatic field at infinity, which is due to this fragmentation inside the black hole, inside this ADS2 space. And then, of course, the symmetries match, or this, yeah. Well, yeah. Let me just wrap up. So, okay, so I described this model with a paramagnetic phase that was similar in some respects to the SYK model, and this spin glass phase that we were interested in, and it has these interesting features of a reparametrization symmetry and gapless spectrum, and there's a Lyapunov exponent. Just a few questions that one could try to answer is, what is a more systematic conformal perturbation theory around this approximate solution? Can that be done in the spin glass phase? Is there anything to this ADS2 fragmentation picture? Can one make that more precise? And then there's also various string theory constructions that one can make contact with. Okay. Thank you.
Great. Thanks a lot, Felix, for the very interesting talk. Is there any question for Felix?
I have a few questions to ask.
Sure.
Yeah, thank you, Felix, for the talk. So one question, like, so you said nowhere the lambda is the lambda saturates the Lyapunov exponent saturates the bound, is it? So wouldn't it then the Lyapunov exponent never saturated the bound, right? In that bell curve. So like, wouldn't it say like so then how wouldn't you not expect a gravity like kind of interpretation then, right?
Yeah. So one issue is that we haven't been able to push the numerics to the regime where we might expect it to be the largest. So we can see here that these peaks, they do grow as we increase beta j. So as we lower the temperature, you can achieve higher and higher values here. Or maybe let me show this thing. So here's this schematic phase diagram where you have temperature and 1 over mj on the axis. And these peaks that I showed in the Lyapunov exponents, they're roughly like on some location here. And it seemed like as you go further to this tricritical point here, the exponent keeps growing, but I can't quite say to how far. And it might be that somewhere here you might expect it to be the largest that you can achieve, but then it's below the glass transition. So some of I think what probably happens is that the spin glass transition happens before you reach the maximal exponent that the paramagnetic solution supports.
So all the Lyapunovs were peaking around a similar value of mj because of this tricritical point. Is that? So in that Lyapunov exponent plot, like all the peaks were around at the same value of mg, right? Are you saying that's because of this critical point?
Okay, so they were roughly at the same value of mj for the cases I plotted.
But that's just
not exactly the same. It's roughly the same, and I think it starts to deviate more as you. Yeah, actually, in the paper we have a plot of where this location is as a function of where this peak is as a function of beta j, and it's sort of, it's not at constant mj.
Okay, and one more question: did you have some interpretation of this the block size m from the gravity picture?
The log.
The block size m, the small m.
Oh. Yeah, I'm not sure. So perhaps one thing one could try is to consider this ensemble I mentioned, where you explicitly clone the system m times, and ask if that gives you useful boundary conditions in gravity. Yeah, one could try that. I'm not sure. This needs to be studied.
Okay.
There's a question by Emil. Do you want to ask it?
Yeah. So regarding this last speculation of ADS fragmentation, so I was wondering if you had thought about this similar sorts of phenomena crop up in other toy models. Specifically, I'm thinking of quiver quantum mechanics models that were studied by Denef and others in the 2000s, where the low energy dynamics has a set of what are called bubble equations in some context, or basically some D-term equations for the quiver, and they have a sort of a frustration aspect to them that you're trying to solve some kind of locations for some multi-center solutions, and they have some interaction due to spin moments that are carried by the sort of cores in the solution. And so there are many supersymmetric ground states that are whose sort of configuration is governed by some sort of frustration. And so I was wondering if that's somehow related to the sorts of things you're looking at.
Yeah, yeah, absolutely. So I have a hidden slide here, which is, I think, what you're referring to, that there are these multi-horizon solutions. And
yeah,
yeah. So if you do this quantum mechanics models, then typically supersymmetry fixes for you the Lagrangian in the usual way, and you have the bosonic part of the potential. Looks like what I have here. And so I think what they did back then, when they made this connection with glassy physics, was they took the large G Yang-Mills limit, where this last term in the potential goes away.
Mm-hmm.
And this last term in the potential, we would like to think of as implementing something like the spherical constraint.
Right.
So the theta are these phi Lyapunov parameters, and the phi are the bottom components of the chiral multiplets. So this is like a spherical constraint, but I think they ignored that back then. So what one should probably do next is try to reinstate that constraint, because it was really crucial in this p-spin model.
Uh-huh.
And then you see that this bosonic potential looks a lot like the p-spin model. There's this spherical constraint, and the superpotential, the simplest superpotential that you can get would be cubic. It's the thing at the bottom.
Right.
I don't touch with my pen. Yeah. So, and then where this omega ijk carries information about the compactification manifold. And yeah, if the compactification is sufficiently complicated, then you can think of that as random. So it's like the random couplings.
Mm-hmm. Mm-hmm. And one other totally unrelated question. So in these spin glass phases, is it understood what the level statistics are?
We know what, I know what they are not are. They're not random matrix theory. They're not the usual random matrix theory predictions.
Mm-hmm.
So you look for deviations from that. Yeah, I wonder if this is known, and I'm not aware of it. Perhaps someone else knows whether there's a specific statistics that one expects. Or,
okay, thanks.
I'm not sure, but you expect deviations from the random matrix predictions?
Yeah, I would think so, because if there are sort of energy minima that are not talking to each other, then there's no reason for their levels to repel.
Yeah.
So can I ask something? Yes. So when you say that you have this emergent conformal symmetry in the spin glass phase, can you say a bit more about it? Like, is there like the same pattern of symmetry breaking as for the Schwarzschild, or is there like a Schwarzschild like action?
Yeah. So that's a good question. So yeah, the question is, how do you derive the Schwarzian? And so one argument would just be that the free energy, you can compute the free energy perturbatively in that limit. And so the standard free energy would go like linear in T. And yes, so it would look like the free energy that you associate to a Schwarzian action. So there's probably a Schwarzian action that describes this free energy. Now, what I'm a bit less sure about is whether that's the right object to consider. So you could also consider this generalized free energy in this grand canonical ensemble that I mentioned, where you clone the system m times, and the generalized free energy in that ensemble actually goes like T squared, and that does not come from a Schwarzian. So if you want to get that, then you might have to write something more non-local, like perhaps something similar to what was done in this paper by Kitaev and Su. But something I would still like to understand is if there's a more direct way to just take the effective action and extract from it a Schwarzian description.
But couldn't you do it if you just know the symmetry breaking pattern? I mean,
yeah. So the symmetry breaking pattern is the same. So you have this reparametrization symmetry, and it's broken.
Okay.
So that kind of argument, and then you can say, and the free energy is also precisely what you expect from a Schwarzian, and we know the free energy exactly, or the linear in T term. So that should tell us the coefficient of the Schwarzian. Yeah.
Another question, have you tried computing the spectral form factor, the ZZ star, which is a signature of chaos if you have the Plato region? I mean, if you have the Plato, it's a definite signature of chaos. Did you compute that?
Yeah, we haven't done that.
Okay.
Yeah, that might be interesting. I don't have anything else to say about it. But I suspect that in the paramagnetic phase, it probably behaves in a similar way as what you mentioned, with a dip and ramp and plateau and so on. In the spin glass phase, I'm not sure what to expect.
I have a naive question, like, so if you have a fragmentation kind of thing, like, what do you expect?
Yeah, I mean, it's a great question. I don't know. So I guess that's really the question here that I'm putting out there. What, how does this work in detail? Yeah, maybe I shouldn't make any wild guesses. Yeah, sorry, I don't have much to say about that. This is really something we would like to work out, but at this point, it's just an idea.
Thank you.
so are there any more questions for Felix? Okay, if not, maybe we can thank him again for the nice talk. So thanks a lot, Felix.
Yeah, thanks for having me.
Yeah, no problem. Okay, so let me, I will end the meeting now.
Okay.
So bye.
Bye.